So what a provocative title. Oh, I'm Jack Kozik. I'm with Nokia. And I actually have a provocative title for you. LTE, frickin'. I was thinking on a timer. He put me on a timer. Okay. LTE is good for smartphones and IoT too. Well, 2 years ago on this stage, a very distinguished presenter said, well, you can't do LTE. You can't do, you can't do IoT on LTE. LTE is for smartphones, big things with huge batteries, and the battery barely lasts a day. Good for watching YouTube videos on trains, but that's not for IoT. So that's pretty provocative in the context of this forum. So I put that up there. No, there's a new standard that just came out in the standards body called 3GP, Third Generation Partnership Project, Release 13, defined a profile of LTE for narrowband for IoT. And so when they say narrowband IoT, they're actually in the standard, they're actually referring to narrowband compared to what LTE smartphones can do today, which is far from narrowband. Okay, so I'm just going to briefly introduce the standard, and the goal here is, as I said, is the standards in the network and in the chipsets to make the already deployed LTE infrastructure, the cell sites, the radios, the routers, the filters, all the software, all that spectrum that's already there, make it more cost effective for IoT. That's exciting. That's good. So exciting. One of our customers, he got up and said, headlines. He was excited. The standards have finally come through. And this was, the standards got signed in June. And one of our customers, he gave a talk on narrowband IoT and how excited he was that now the next release of the standards has the capabilities being built into LTE, so that the new LTE build-out that's happened over the last several years can be a home for new IoT devices. And so for those of you in the room, did you miss the excitement? Well, it was pretty exciting, but it was in the trade press. There was trade press. Vodafone was interviewed, and they said, yeah, the new narrowband IoT standard, it's going to crush LoRa and Sigfox. I said, oh, that's pretty harsh. Whereas LTE is a cellular technology. We're all using it, right, for our mobile phones. People who are building brand new Internet of Things applications turns out are using competing technologies. They're using radio technologies called long-range unlicensed radio called LoRa. In Europe, there's widely deployed unlicensed spectrum solutions using a technology called Sigfox. And so while LTE is great for consumers and people, other Internet of Things cellular technologies are being deployed in competition with cellular networks. And so, in a way, this new standard is in response to and to help cellular networks stay competitive with unlicensed spectrum innovations. People know LoRa. If I said LoRa, no, LoRa. There's people doing, you go into Hacker News, you see people talking about doing LoRa applications and LoRa drive testing in San Francisco and stuff, long range radio. It's think Wi-Fi about long range, right? For Internet of Things devices. Okay. In the last trade show conference for the industry was in September, and chip vendors like U-Blocks. Is there a Sequence guy here? No, he's probably in the other room. Let's see. The chipset vendors have come out with narrowband IoT chipsets now. And can you, I'm not going to open up my phone. Maybe when you go home, open up your phone and take a look at your chipset. There's a lot of chips required to talk into LTE. LTE devices have 20 megahertz of radio capacity, has multiple radios in it. In order to get 100 megabit per second download speeds, you need to have lots of power, lots of radios and chip capabilities. The narrowband IoT standard means little tiny chips, really low power. And so this company here as well, where they're advertising their chips because they want new developers to put stuff in. On the previous chart here, I snuck the Sequence logo and I put a picture of their narrowband IoT chip in there. All right, so that was sort of the headline. What's the motivation? What problem we're trying to solve? The market window right now, especially in North America, especially in the U.S., certain mobile network operators have plans to sunset their GSM services, and on just like the majority of IoT devices that are connected to cellular networks today are based on GSM technology. Well, GSM, you remember the 2G technology? Remember when you had? Well, it's probably a Nokia phone. Your 2G, your Razor. Remember your Razor? Remember how skinny and small they were? Remember how small well, you didn't open up your Razor. If you try to remember 2004, if you opened up your phone back then, there's just nothing in it. It was light. It was just bare metal. Right? Those chipsets are in IoT devices by the tens of millions in just the United States market. Or around the world, billions of those chipsets are in for devices that are connected to cellular networks. And that network is being shut down. And those device developers are redesigning their devices. And what technology are they going to use? Well, they're going to use LTE, right? Well, LTE is really big and heavy. Well, now with narrowband IoT, the sunsetting of and the retiring of the older devices in the cellular side will be renewed, but onto an LTE radio. So that's good, right? Maybe should have happened quicker. Okay, so cellular networks, the cellular network operators, my customers, know that LTE is not the only game in town, and so they're feeling a little bit of pressure. And as a vendor, I want to make them happy, and so we're working on the cellular side, not the device side, the cellular side of implementing those standards. And so if I may give myself or the industry some credit, the standards for creating narrowband IoT had market pressure such that the standards for them were done in record time. And of course, we grade ourselves, and so maybe independent valid verification would be needed there. But this is something that the market need was identified and standards were written, and now chipset vendors are building things in relatively record time. So the telecom industry as a marketplace wants to keep IoT devices on their network and attract even more. And we know, you can just do everything in Bluetooth or Wi-Fi, right? Well, there's lots of places where people are building applications where they require some notion of a cellular technology. And mobile network operators are putting in place developer programs to encourage new devices to get connected. Mobile network operators and vendors are defining device profiles to make it easier to connect those, more cost effective to connect the devices in, and are defining new architectures in the network to make those devices run at even lower power. So let me just briefly review, just so you know, some examples of some of the requirements for these devices. Use cases, public safety. We had a lot of use cases already discussed. Chuck gave a lot. Everyone had a lot of use cases. I get to put a couple of mine up too, just so you get. Narrowband IoT has got its space. Connections for public safety, connections for digital health, connections for various different kinds of mobility. And I give the example of highway up here. Connectivity for utilities, and the building blocks for doing smart cities. These are example use cases where a narrowband IoT or the evolution of cellular technology is being made more cost effective. Oh, there's like a whole package. It's a really interesting story of smart parking. People are putting basically cellular radio sensors in the asphalt for parking lots, so that you can tell where there's parking spaces and how full the parking lot is. And the devices are put in, they're like that. Can you see how big that is? That's small. They're stuck in the asphalt. And their design is roughly for the battery, well, we have to prove it yet, but the battery lasts 10 years. You don't stick the parking lot sensor and the charger at the end of the night. It's stuck in the asphalt, and if it busts, you dig it out and put a new one in. But you have sensors. You have sensors spread out through parking lots, and you want to be able to find out how many spots you have open. So you put the sensors around in different places, and you use LTE technology, and sometimes in some places you use LoRa technology to get the sensors to report whether there's a car in that parking spot. I just give this example. There's a whole nice story around this, but this is examples of people who have business cases to solve particular problems where they need cellular technology as opposed to competing technologies, where the need for lower cost chipsets become a factor. Okay. I don't recall, Chuck, you must have had some medical something or another. We have a whole bunch of use cases for medical technology and remote sensor or remote sensing of health telemetry. In these cases today they're being paired with someone's smartphone. The vision of the future is these devices will talk directly to the cellular network, skip the smartphone, skip the hassle of setting up the smartphone to talk to them, because the chipsets will be so low power that you can connect directly to the cellular network without having to pair it with your mobile device. Another example use case. For the cases that we're talking about for the telemetry and sensor data, yes. Yeah, I can hear. Fine. Which one are you talking about? So it could be a device to device, but in this particular case, it's simply imagine the application of tracking cars for credit challenged car sales, where you're just trying to keep track of where your cars are, so that if the person doesn't pay the bill, you can come collect. There's 5 million cars that are sold that way in the U.S. every year, with some kind of a fleet tracking for credit challenged car sales. That was that particular example. But of course it could be all the other variations, but that was the particular example that was mapped to. Any questions? Okay, thank you. Okay, so in the telemetry case, the devices in some cases may only send a very small amount of data very infrequently. Everything from telemetry from water meters to sensors out anywhere. You could have devices that wake up once a month, send data, go to sleep, and you don't hear from them ever again until the next month. Very low power. Not the way mobile phones were designed for people. Okay, that's one case. Same model, but infrequent data. Say, for example, the vending machine or the smart meter. But in this case, I get local power. If I can get power, oh, thank goodness, I get power. Some cases you have requirements where the batteries have to last for 10 years. Okay? So this is the use case of, I'm on a timer again. Okay, now I'll transition. Or in some cases you really do have local power, but the same chipsets sometimes need to have a higher data rate. Smart city traffic or security cameras, you need to have devices that can not only handle the low power case, but you also need to be able to support what I would consider things closer to what a normal cell phone would be able to do. I guess I should have checked for timers, huh? You think so? Or are you doing? Let's see your hands, Jack. Okay, so anyway, I have use cases for smart home. The other use cases, different from a cellular technology, I have devices that aren't moving. So I build this whole cellular network, and I built inside it the capability for mobility. What happens if I add 10 million devices to my network and they don't have any mobility? Well, cellular networks are designed for mobility. I need to be able to have a way of cost-effectively adding devices, but not engineer a whole bunch of mobility capabilities into the network for them that never gets used. So I have a challenge there. That's an interesting dynamic. And I summarize all of my various different requirements on one table, where the message here is a designer of a network for IoT has different requirements than if I'm designing a network for people. Very low mobility, potentially very low data, very high. Many use cases require very lengthy periods between changing batteries. And the Narrowband IoT use cases that the standard was specified for are put in place to handle these different device profiles and different power consumption models. So if I take a look at humor me here, there's numbers on here, these are worth looking at. If I take a look at one of my mobile phones today, I don't know, do we have, I guess I thought I had a Cat 5 phone, but this is for this table, mobile phones today are category some large number, like category 4. And those are big, beefy smartphones capable of doing Netflix or YouTube while you're on a train. The downlink capacity is 150 megabits per second. The uplink peak rates are 50 megabits per second. They have 2 antennas. They operate full duplex. And the actual, like the antennas and the radios are designed to receive, transmit cumulatively across 20 megahertz of bandwidth. Well, you need that much if you're going to watch, if you want to watch cat videos, right? You need that much. Okay? The way the specs were written was like, well, instead of making a bigger phone that does even more and more, instead of doing a phone for doing 4K videos and some kind of immersive thing at the higher end, instead of making higher end, let's scale down. So in the standards, they define 2 new categories. It's, category 4 is big, category 3 is less big, category 2 is less big. Category 0, well, no, we want something even smaller than category 0. We want a category M, for machine. And the category M devices are chipsets such that, and the network such that, the peak downlink capacity is only 1 megabit per second. 150 times less than an LTE phone. Boy, that's, not you're decapitating it, but that's what's required. If you want things to be cost effective, you need to get skinny. And number of antennas, only 1. Instead of full duplex, you transmitted half duplex. And the actual inner guts of the radio inside the device is only 1.4 megahertz of capacity. And by some sort of subjective measure, the modem complexity compared to today's smartphones is 20% as complex. It's simple, relatively speaking. And then there's even another one, and you see the buzzwords, the Cat M, and then the Cat NB or Cat NB1, where you have a device that scales all the way down to 180 kilobits per second or 200, and has an uplink peak rate of only 100 kilobits per second. My God, that's so slow. I got this brand new LTE network that has so much capacity. To make it cost effective for IoT devices, I need to have a profile that's skinny down. That's skinny down to be the same basic capacity as those 2G Razor phones you had. Well, some of you are so young here. You didn't even have Razor phones. Right? Your parents. The design of the narrowband IoT is actually bringing the capacity of that LTE network. It's basically a collection of subcarriers. Basically, you give one subcarrier to the device to make it really skinny. So you match the power profiles, the power profiles, and basically the speed profiles of GSM GPRS. For those of you who were all excited when you stopped having to do GSM GPRS, well, Narrowband IoT is bringing that capability back on top of LTE networks for the benefit of all the Internet of Things devices that are coming out. Okay? Let's see if I can find what the right summary slide is. So this is probably a good summary slide. So in the spectrum that makes up LTE, the 4G technology we're all using, the way the standards have always been defined is you can use a variable amount of spectrum over the air to the device, and every year we keep adding more spectrum with carrier aggregation and LTE Advanced to make it faster and faster. Well, now we have a breakthrough. we're going skinny. And the going skinny is Narrowband IoT, Narrowband IoT. The buzzwords from my presentation here, Cat M1 and Cat NB1. You see those buzzwords as far as devices go, and the ability for mobile network operators to deploy services more cost effective in the IoT space continues to, their reach continues to broaden with advancements in these standards. For this audience, for this talk, this is all the more I was going to cover, Manny, on this. Introducing the topic. For anyone who wants to know the next level of detail, I have lots more detail, but I want to know that unlike what was reported here 2 years ago, LTE is on a path to become even more cost effective for IoT. And yes, it's good for smartphones, but it's good for IoT too. Thanks very much. Questions, comments? Oh, Chuck has questions.
Nicely done, Jack. Some might argue that it's wasteful to use this precious mobile spectrum to talk to things that are buried in concrete or hung on the underside of bridges or stuck to a street lamp pole somewhere, which is probably 80% of those 50 billion IoT devices we keep hearing about. So if I was a network operator and I had a certain amount of spectrum that I preciously licensed, and I could use a chunk of that spectrum to provide one really nice 100 megabit download, or to run 100 parking space sensors, because the ratio looked like it was about 100 to 1 in terms of the spectral utilization. Which one should I do?
Okay, so it's all about engineering economics, right?
Yep.
If you wanted, you could make those sensors all Bluetooth and have one gateway someplace.
Right.
Right? It's all about engineering economics. You can make all those sensors LoRa sensors and run through a LoRa gateway.
Yep. Okay?
The way this works is you've already got the spectrum, and the devices either land on your, if you're a mobile network operator, the business case is the devices either land on your network or they land someplace else. And if there's money to be made, then you want to have an architecture that's cost effective to make it. If there's no money in all that, then just put in LoRa and put in Bluetooth and have it. So the use cases that we're talking about are places where people want to pay money.
Right.
Okay? Now, as an engineering side effect of the way the standards are defined, the subcarrier can be swiped away from an in-band spectral block. Since you asked, he asked this. Okay. You take an LTE spectral block, you can take one little subcarrier out of it and say that's my narrowband IoT. So basically, your spectrum, you don't have to get any more spectrum to do this. Okay, and since you asked, Chuck, you can stick the subcarrier for narrowband IoT in the guard band. Just the way the standards went. You can stick it in the guard band.
So it is, quote, free.
So nothing's free.
I understand.
Nothing free, especially from the vendor who sells it. What can I say? But since you asked, the engineering economics for going after some of these sensors networks, there's a crossover that shifts when you bring technology in here. In some places you say, nope, only business I'm ever going to do is having kids watching cat videos. I'm going to do really, really good high definition video to mobile phones, and that's my business. With the narrowband IoT, the crossover where you can use that LTE spectrum for more things changes, and you just simply follow the money. And where the places work, you now have a crossover where they work better, and where the places where they don't work, well, they don't work.
Okay, one other question, hopefully quicker. do I have to do anything to my cell sites to make this happen? So let's say that I want to launch a fleet of 10,000 weather balloons, each of which equipped with one of these modems, and fly them all over the place, and wherever there's a Verizon cell, I want to receive those. Do I have to go around to thousands and thousands of Verizon cells and put a little software change in or hardware change in?
So the short answer is it's a software change, but it's actually more complicated. You asked for a short answer. Cell sites are pointed down, balloons are up. Okay, so
I understand that.
Pardon? That's it. All right, very good. Thank you. Thank you, everybody. Have a good afternoon.
Thank you.